about a week ago, so it's better to make a refresher, and it will take substantial time. I'll try to scramble it and go quick, but it's not easy. Just if without explanation, if you just verbalize all things, it will take time. So there will be two things that we need to take out of the classroom. Take home message. Maybe even one. The concept of Slater determinant. So if you have heard about it before, give me a little sign. 1, 2, 3, 4, 5. Okay, if you never heard about Slater determinant. 1, 2, 3, 3. Who heard but not sure? Okay, well, 3. So it's a perfect audience. So most of you were exposed. So I'll give brief introduction because slides may stop us from true interactive communications. We did finish everything, well, not everything, but necessary minimum for nuclear degrees of freedom. We agreed that they are point charges to good level of precision. Now we need to focus on electronic structure. Again, we have a challenge of a really huge number of electrons, right? And I'll show some examples to see how terrifying it is. Arguments that it is not tractable by modern computations. So one needs to stay on the road of ancient Romans, divide and conquer. So we divided electronic and nuclear degrees of freedom. Now we need to split electronic degrees of freedom on something simpler. So we need to go from multi-electron wave function, if possible, to one electron wave function. It's not always possible, it's not always correct, but it is only the way to survive. And we already discussed about separation of variables, of representing wave function of many variables as product of functions of single variables. Okay. So we did. And we are going to practice similar thing for electrons. But electrons are fermions. They follow what was ordered to them by Pauli, exclusion principle, that you practiced in kindergarten when you were filling atomic orbitals with electrons, right? And due to this exclusion principle, one cannot immediately practice product of one electron wave function into multi-electron wave function. There are some advanced rule which is named Slater determinant. So if you are taking notes, you may try to record this idea by your own words. So take home message from today's meeting will be a rule how to compose multi-electron wave function of single electron wave function. And it will be similar to product, but not product. I hope I intrigued you enough. So if you look on the handout that was distributed, it is related to Szabo and Ostlund book, and it takes a really high-speed interstate highway. We do not need to drive so quick, but if I miss something or you do not trust me, you can browse through and see how they go through this material.
So we're trying to make a more complicated system less complicated with describing the electron. So going from multi...
I hope I understand you, and I hope you are telling the right things. Please repeat.
So we're going from you said a multi-electron system down to a one.
Yes, from more complicated to less complicated, yes.
And this will describe our system in a way that's easier to interpret, maybe, or kind of...
The question is easy to interpret, yes, but in addition, there is a more important thing. If we do not practice things that we are going to do, the problems will be unsolvable at all. So it's not a question of comfort, it's a question of survival.
Okay.
And if you browse through handout materials, you'll see that, okay, I need to be more organized and give more heads up before. So the goal of the chapter that we are covering, let's go here, is Hartree-Fock theory, right? So it has two names. And the first designer of a theory, the first name, did traditional mathematical physics separation of variables, or product of one electron into multi-electron. And this theory is nice to study, but it fails in describing many phenomena. So the only contribution of, so we will be studying Slater determinant, and contribution of Fock to Hartree-Fock theory is just to bring Slater determinant into here. So he was not designing things. He was just transferred one concept into another concept. And it's enough to memorize his name forever, because it gives qualitatively correct results. Right now, later on, we will use much more correct and practically reasonable theories, but this one is the simplest possible rigorous.
Does this follow force field? Like, would force field kind of be first and then Hartree-Fock?
No.
Okay.
No. It's good that we are speaking freely. We are departing from nuclear degrees of freedom. We will nail down positions of ions and forget about their ability to move for like 2 months.
Okay.
Like, it's a game for kids, freeze. So all ions are frozen, and only the electrons can do something. Okay. And also, I'm kind of recalling for myself, before we go to the take-home message, there will be a quick recall of the atomic orbitals for hydrogen, which we all are supposed to know, but just in case, it will be a quick recall. So here is John Slater, who did several contributions, and I know why David declined to travel to Sanibel Island this year. He probably got feared to die there. No, there is nothing scary there. You were there.
I was there, yeah.
So it's a quick overview of what we did before. So we did form the atomistic model when we quantify. Thanks so much. When we quantify positions of nuclei and electrons, and then they are used to form the Hamiltonian, and then as a major outcome of our chapter 1, that we were able to separate nuclear and electronic degrees of freedom. So for electronic degrees of freedom, we have 3 terms in Hamiltonian: electronic kinetic energy, electron repulsion, and attraction of electrons to nucleus. And for nuclear degrees of freedom, we formed Schrödinger equation. We went from time independent to time dependent. We made classical path approximation or point charge approximation, right? Instead of expectation, instead of nuclear wave function, we went to expectation value of nuclei, and then we derived equation of motion for this average positions. And in your homework, you were optimizing them for oversimplified model, right? So from now on, we have basic idea how to optimize geometries, and what are they have equations that rule positions of ions, do keep some contribution from nuclear degrees of freedom. So this energy includes, I do not see this equation here, but it includes nuclear repulsion and eigenenergy from electronic degree of freedom, right? We went through it before. So for the sake, even if we are looking only to optimize geometries, right, we still need to solve for electronic states. And before we were assuming that solutions are provided by someone. Now we need to look how to develop them. So our Hamiltonian becomes simpler, only 3 terms, right? All ions are just point charges. So our goal for next, whatever, a little less than a month, is to find these wave functions and these eigenenergies, right? And previous homework, you were bringing images like this. Okay. So it's homework. So we are going to keep kinetic energy of electrons, energy of electrons interacting to each other, and energy of electrons interacting to nuclei. And before, if there would be no molecules in the universe, this class will be cancelled, right? Because if there are no molecules, then there are no chemistry and there is no computational chemistry. So some physics classes will be still allowed for atoms, electrons. But before we go to molecules, when several atoms are collected together and have shared electrons, we may look onto single atoms and just quickly overview the eigenstates of electron in the hydrogen atom or hydrogen-like atom which has bigger charge. Why we need it? We don't need it. It's easy to assume that you all know it, but we better declare it quickly so that we speak on the same language, right? So before going to hydrogen, I promised a quick scary story. So why computing electronic structure is so scary? Why it is scary for programmers and for computers and for humans? So let's practice the same game as we did before. Assume that we do not know and we do not like math. That we maybe some of you have hidden love to math, but we will hide it. So our goal is solve everything numerically, which means discretize any independent variable and compute values of any function at any discrete values. So just for easy estimate, let's assume that any Cartesian coordinate, Cartesian projection for position of electron is discretized over 10 grid points, just because of 10 fingers. And because we have a decimal calculational system. Then for hydrogen atom, how many independent points we need to represent wave function of hydrogen? If for 1 degree of freedom, we have 10 points. For 1 degree of freedom, 10. For 2 degree of freedom, it will be 10 by 10, 100. For 3 degree of freedom, will be 1,000, right? So if we need to solve for hydrogen atom, we can just split space around nuclei on grid points, write Schrödinger equation in numerical form for each point, solve them, and represent as such cube files, right? It is possible. We can record them in Excel, we can analyze, we can do anything. No problems. If it will be either helium atom or H2 molecule, there will be 2 electrons. And if you split space on 10 grid points, and we have 3 times 2, so 2 electrons, 3 Cartesian projections for each of them. So 6 degrees of freedom. So it will be million points, right? So if we go to atomic carbon, not a molecule, just single carbon. So what did we learn in the kindergarten? 1s2, 2s2, and 2p2. 6 electrons, 3 Cartesian projections for each of them. 3 times 6, 18. So 10 to the power 18. It's amount of grid points that we need to set up equations to solve just for carbon atom, electronic structure of carbon atom. And terabyte, how much is it? 10 to the power, how many bytes? 12? 10 to the 12? That's right? So 10 to the 18 will be just a million terabyte. Like a terabyte is what you can go into store and buy a drive. So you buy a million drives and you are able to describe carbon atom. Right? Nice. And then if you just need a pathetic acetylene, I even do not want to pronounce, 10 to the power 42. So it will be too much hard drives just to store the wave function. So the goal of this slide is to scare you. I'm feared of. So it's a literal recording and solution of multi-electron wave function is a little expensive for us today. Especially if you want to go behind 4 atom molecules. Right?
Basically, the point is to show us that computers don't have enough computational power to solve the Schrodinger equation for a huge number of electrons. Okay.
Yes, yes. So, but we are so brave that we just will design tricks to avoid this barrier. So what we understand under this phi sub a is function that depends on position of each of ions and each of, not ions, electrons. And each vector means 3 Cartesian projections, is what we just covered. So what do we do when we have function of too many variables? Separate variables. We want to represent this function as product of some simpler functions of each of these variables, if possible. Right? And we are going to practice this idea and get some moderate success. We just need to do it carefully. Whatever we will be doing will be not rigorously correct. We will not get absolutely correct answer. It will have some level of precision because electrons interact to each other and they're not independent. So even with all care, the representing multi-electron function as product of one electron function, even with tricks, with later determinant, is not an absolutely correct thing. But there is nothing else to do. I'm going So when I was offering this course for the first time, I went to a conference and a postdoc from my group was giving this lecture. And he did nice slides, so I'm still using them. So our Hamiltonian does have 3 terms. Kinetic energy of electrons, attraction of electrons to nuclei, and interaction, repulsion of electrons. If it is hydrogen atom, which term do we drop? First, second, or third?
Third.
Correct. Thank you, Kevin. Why? Because there is only one electron. It doesn't interact with other electrons. If it does, then it is self-interaction error. Okay, so we drop third term, we have only two terms, and it is one of the few problems in the world that can be solved mathematically correct, absolutely precise. Again, we are not in the math class, so we don't care about solving it. There are some classes that solve it, but rigorous, careful solution, it takes at least a month. If one doesn't skip steps. But the solution is possible. And at least every one of you is aware with this notation, right? So wave function has how many quantum numbers? There is a little lie here. 3, right? 4. Principal, orbital, magnetic. Magnetic is favorite quantum number of gauge, right? And spin. So let me see if it can. No. I do not like these figures in this discussion, but we need to do it once. So if you measure distance of electron from the center of hydrogen atom, there are eigenstates, right? And they differ by quantum number, principal quantum numbers, right? Another thing that so it determines the energy. Then in addition, the electron may rotate with different pace, having different angular momentum. This second quantum number, orbital. And then for the total amount of kinetic energy associated with rotation with angular momentum, it may be oriented differently in space, have different projections on specific axes. This will be a magnetic quantum number, right? So, and the mathematical solution for this is obtained as product of two functions, one of which depend only on distance from center, and another is function of angles, right? Why two angles? Because, yeah, it's nature of Fox field. And each of these functions are mathematically rigorous. They can be expressed analytically, at least through series. So there are spherical harmonics for angular dependence and Laguerre polynomials for the radial part. And most interesting part, this polynomial is hidden, but it is known. And when we draw orbitals for hydrogen atom, we basically practice this function. So intuitively, all of us know how they should look like, right? A little comment that is always, not always, but often skipped in the when people try to draw atomic wave functions. The solutions for spherical harmonics do have their imaginary. The dependence on magnetic quantum number accumulates phase as one goes along this azimuthal angle, right? But humans like figures without imaginary numbers. So what is done all the times and hidden from attention of students is that one takes solutions with opposite values of m and then add or subtract them. So when we draw p or d orbitals, it is the result of this procedure. When you add or subtract Well, when you subtract, you need to divide by imaginary unit, but the wave functions that one draws, they are real, right? So there is a procedure how to convert two imaginary functions into two real functions. Who we are and what are we doing? We want to describe multi-electronic wave functions for any molecule. Our goal for today's meeting and take-home message will be Slater determinant, which is a procedure how to construct multi-electronic wave function out of single electron wave functions. And on the way to the Slater determinant, we are going through a quick recall of the atomic wave functions, because they will be building blocks to form molecular orbitals. Well, molecular orbitals not today. Multi-electron wave functions.
So anytime you see one that's has a negative I in there, you're gonna do the opposite. You're gonna make it easier to add.
If you need to draw it.
If you need to.
If you need to do some mathematical operations, imaginary unit and functions of imaginary unit are really comfortable.
Okay.
Because they're easiest thing to integrate or differentiate.
Okay.
So, who never saw these images? Who is very comfortable and can explain what they are? Okay. So about half happy to explain. So what are they?
Molecular orbitals.
Huh?
The molecular orbitals.
Which orbitals? Is it right?
Atomic.
Atomic orbitals.
Thank you.
Okay.
Atomic orbitals.
So what are the axes? So orbital quantum number and magnetic quantum number. So we are neglecting dependence on the offset from the center, just looking on the dependence on angle, right? And the states with small principal quantum number do not have comfort to practice different other quantum numbers. For lower state, you have only one. But as far as you go up to larger and larger principal quantum number, you cover more and more these exotic shapes, right? So it is what you saw as S, P, D orbitals, right? One first shell has only S orbitals. For second shell has 2s, 2p. So this indices 0, 1, 2, 3 correspond to SPD, right? And the magnetic quantum number corresponds to which part of kinetic energy of rotation corresponds to rotation along z-axis, right? So if all kinetic energy of rotation is represented by rotation around z-axis, so it will be around z-axis, then fringes, positive and negative, will go across this path. If there is zero projection, if there is no component of kinetic energy associated with rotation in the xy plane, there are no nodal points, nodal planes as we go across. All the minima and maxima will go only as we change angle theta, right? From top to the bottom. What else? Who did hear and practice the word isosurface?
Say it again.
Isosurface.
Isosurface.
1, 1.5, 1 2/2. Who never heard the word isosurface? Majority. Okay, so the atomic orbitals are three-dimensional functions. They're defined in each point of space. But it is quite complicated for humans to visualize it, right? One needs like to have a fog, clouds, right? And instead, there is a way to represent three-dimensional objects by selecting surface of the equal value of a function. So it is a surface where we have probability density or amplitude of probability density, let's say 1%. And then it will form these shapes. It means inside these shapes, it will be higher density, outside sparser density. But these balloons are a little easier to represent compared to three-dimensional shapes. Make sense? And we did miss dependence on the offset from the center. So for the simplest one is orbital. We again, this if you are tired, lean back and relax. I will let you know when to wake up and when there will be most important message, and it will be about way to determine. Now we have just a little decoration.
So the sorry,
yes, please,
so
please.
So the isosurface is the probability of where the density would be. It's more kind of like a cloud, not so much more a discrete kind of low, what we see with the atomic orbitals.
We will go through this concept several times. So if you have one-dimensional function, and we set up a threshold value, so we pick up only values of a function where function equals this, let's say f0. So it will be points, right? Now, if we do have two-dimensional function, x1, x2, right? So it's complicated.
So it's kind of like a contour map. Kind of.
Contour map is a surface in two dimensions.
Okay.
1D, 2D. Then we set up f0 value. We draw a plane. Do we have another color? Okay, I'll try to be artistic.
Oh, I see.
So a line where function is equal to predetermined value will be isocontour. So here may be iso point, here will be isocontour. And if it is a three-dimensional shape, which is really hard to draw, we can also select such object in space where function equals to predetermined constant value.
Right, and it's a slice, so you can slice it.
Slice from
different
slice.
to get.
See, we go from one dimension to point, which is zero dimension, reduced dimension. Here we go to two dimensions to line, which is one dimension. In the three dimension, we go to 3 to 2. So we go from three-dimensional distribution to two-dimensional surface. And iso surface is just from 3D to 2D.
Okay.
Okay. Where we are? So wave functions, psi, n, m, l, and we skip spin for now. Product of radial and spherical. Theta, right? So we already discussed the spherical part, and now quickly focus on the radial part. So it is how the radial part of wave function depends on position. For the lowest state, for the 1s orbital, it has maximum right at the atom, and then as we depart from center of the ion, the wave function departs, right? If we are going to (2s) orbital, so next principal quantum number, and we have dependence on the position, which also has maximum in the center, but then it has one minimum and then another thing. Right? If we go to, so here this function has two indices. One is principal quantum number, and another is angular orbital quantum number. So for the p orbitals, it has 0 probability at center, and then some non-zero value in between. Right? Make sense? So this p orbitals are like petals with nothing in the center.
So orbitals are basically probability clouds?
Amplitude of probability. So orbitals are such objects by taking absolute value square of which we get probability. Okay?
Okay, so
Square root of probability, but do not, I should take microphone off. Do not repeat it, it's only for development concepts.
okay,
So orbital is square root of probability, but never say it in public.
all right.
Okay? By the way, if you still have time, if you are tired, and I can make a little break in the presentation and go online and suggest you a nice website that everyone, I promise, will entertain. Did you ever looked at p-table? You did. P-table. So if you select orbitals and you click on hydrogen, and then you look for, since it is one electron, it is in the lowest state. But here, as we go higher up, it will be different principal quantum number, and it will be different values of orbital quantum number, and these cells will be different projections of the magnetic quantum number. So just by browsing through different cells in this table, you'll see shapes of orbitals. It's not isosurface. They try to show three dimensions. So lowest state has quantum numbers 1, 0, 0. And then if we still have 0 angular momentum, it has like one sphere inside another sphere. But if you go to p orbital, it is your favorite, how to say, gym exercise too. Just oriented in different directions. And if you go to next, there will be opportunities not only. You see, these p orbitals have some structure as you go between center and outside. So there's additional fringes because of the radial part of the wave function.
So this means the probability is smaller in the center than it is in the outer parts?
Yes.
Okay.
Yes. And then there are d orbitals that some of you may like.
And are we assuming that all electrons are constantly moving through all of these, or is it just like two are only in that zone?
Great question, which is really challenging.
So on one hand, we believe in stationary Schrödinger equation. So if you place electron into orbital with certain quantum numbers, it will stay there forever. On the other hand, there is a time-dependent Schrödinger equation, that as time passes by, there is accumulation of mass. Even if distribution stays the same, there is a dynamic. Maybe it is not reflected in any observables, but there is a constant accumulation of phase.
Constant accumulation.
Accumulation of phase is multiplying by e to the power imaginary unit times energy times time. So if you take absolute value square, it will give you constant. It will not change anything. But there is a dynamic. So electrons move, we just do not see. Okay? And interactions, yes, they repel each other, and they, on the lowest order of description, they kind of coexist in different orbitals. But as soon as we bring in more and more electrons, they start to repel each other, start screening each other, and there are additional effects. If you were asking about this. Yes?
Okay, I sort of have I don't know, a silly or elementary kind of question. Where we have unpaired states, is it going to matter in terms of, I feel like I kind of know the answer to this question. Unpaired electrons, some are so important versus others, depending on which shell they reside in. Because that's going to make a difference in the energy with interaction moving them around.
Electrons like to be paired.
They like to be paired.
If they are unpaired, there are additional energy penalty. If it is transition metals or lanthanides, there are additional rules of filling shells. So, in some circumstances, they like for the high orbital momentum orbitals, they like to be unpaired first. And if you enforce them to be paired when they do not like it, there will be another energy penalty.
Got it.
And this Aufbau, you all have heard the Aufbau word, right? Which means like built on in German. So it's like how this cells are filled with electrons. And if you practice this website, you'll see these illustrations for the orbitals, right? Okay, enough for relaxation. Let's go back into the class material. And I do have a sign that voice is not recorded, but at least the images will be recorded. So, who we are and what are we doing? Our goal is slightly determinant, to build multi-electron wave function as something like a product of atomic orbitals. Atomic orbitals are our building blocks, right? And we will want to bring together several atoms, form molecule, and then tell that electronic state of the overall molecule will be built of products of atomic orbitals, as much as it is possible.
So each atom has its own atomic orbital?
And each of them, most of atoms have more than one electron. So,
Okay.
so some of them are occupied, right?
Also, each electron in each atom has its own orbital, and they combine to form molecular orbitals?
Yes.
Okay.
Well, molecular orbital is an approximate concept. The more rigorous is multi-electron wave function. Okay. Who can tell about antisymmetry? Who took undergraduate PChem 2 for statistics? 1, 2, 3, 4. So, what is antisymmetry?
Isn't it like the literal opposite of symmetry, where symmetry is it's the same reflected, but
Does this have to do with point groups?
Okay, nothing wrong. Everything correct. Let me be more specific. What is antisymmetry of electronic wave functions? And how it is related with Pauli exclusion principle?
Is this chiral?
isn't it when you switch electrons, you have to introduce a negative sign?
Perfect. I cannot write by finger, but Ben 1+. Good. So, before we start building multi-electron wave function, we should make sure that they follow this rule of antisymmetry. And if you glance through this handouts, you'll see things about it. So, when we swap order of electrons, like probability distribution shouldn't change, but the sign of the wave function must change. Why? This is a really terrible and, how to say, counterintuitive question. Do you know, if you have the answer, some of you may explain it better.
What was the question?
Why swap of the order of electrons in the wave function must change the sign of the wave function.
Well, I guess the wave function seems to be going up and down, so changing above a zero mark, below a zero mark.
That's just angular momentum.
No. I like what Midi is telling.
Does that make sense?
It does, and I will try to show it. Maybe it's time to write a couple of equations. It's really a counterintuitive part, and I will try to cover part of this is covered in slides, but first I may draw. So we need a property that if we swap the order of electrons, then the sign of a function will change. This is not a frivolous wish. It is not because I have a mood to change signs of wave function. It is literally dictated from Pauli exclusion principle, which is that two electrons cannot reside in the same quantum state, right? So I'll show a couple of slides, and we may come to the proof of this statement. And this is a true challenge.
Does this have to do with state functions? Or no?
No.
Okay.
It is used later for
Okay.
for many things.
Gotcha.
So it is what we want. It is not a proof. So we do want change of the sign of wave function and keep the probability distribution, wave function squared, upon the swap of the order of orbitals. So can we try to compose, to do a little mathematical experiment? Suppose that we already have orbitals, phi 1, phi 2, and we do want to compose our many electron orbital as a product of such orbitals. So let's just make an experiment. Phi 1, phi 2, in positions R1, R2. Minus phi 1 R2, phi 2 R1. So in these terms, we introduce two terms, and you see that here the indices coincide. So in the quantum state number 1, there is electron number 1. In quantum state number 2, there is electron number 2. And here, in quantum state number 1, there is electron number 2. And in quantum state number 2, there is electron number 1. So we swap the order. Let's inspect what happens if we swap the order of electrons. So it's not a proof, it's a mathematical experiment. It means I cut and paste. I swap order of electrons here and swap order of electrons there and see what happens. Let's just try it. So phi of R2, R1, and here let's follow this rule. So phi 1 of R2, phi 2 of R1. No errors, right? I just practiced this work. Now here, minus phi 1 R1, phi 2 R2, right? And now let's look how this original term corresponds to first term in the first line corresponds to the second term in the second line. Do you see any difference or similarity? Huh? They're the same with, but there is a minus sign. Now let's circle this one and this one. Second term in first line and first term in second line. Are there similarities? They're the same, but they have different sign. So now we can write down that phi R1, R2 equals minus phi capital R2, R1. Right?
Also, that's anti-symmetry.
Yes.
Okay.
Anti-symmetry of wave function. And if you really want to be picky, we can put brackets and put square 1 over square root of 2 for later normalization. Now, there is one trick that I fear to do and declare and to do. What if we will be so brave to not obey Pauli, to violate his rule? How can we do it with this writing? So here I'm trying to violate Pauli, not Pauli's rule. I still have 2 electrons, first and second, but I will try to squeeze them into the same state. So this will be wrong, R1, R2. Now I will practice the same style of wave function. 1 square root of 2, phi 1 of R1, and then not phi 2, but phi 1 again. Phi 1 of R2, right? I'm placing both electrons into the same quantum number. Minus, and then I'm swapping phi 1 of R2, phi 1 of R1. Same wave function, but 2 different electrons. What will be the answer? Huh?
Yeah.
Everyone agrees? Right? So it's the same function. Phi 1 R1, phi 1 R1, phi 1 R2, phi 1 R2. It will be 0. And wave function must be normalized. It must be non-zero, just by definition. The integral of wave function should be number bigger than 1, bigger than 0. What does it mean if you get some wrong answer? It's not from this story, not from this movie. Something is wrong. It's not allowed here. So if we accept this rule, which later we will call Slater determinant, we will automatically see that this rule will prevent us from violating Pauli's principle. Right? So if by some occasion our solutions will mandate us to violate Pauli's principle, no such solution. So it's how to say, additional measure against violation of Pauli principle. So if we assume this form of wave function. And I think in previous year, it was much quicker. If replacing index 2 by index 1 here, and index 2 by index 1 here, when it's getting 0. so I can deliver it much quicker than rewriting stuff. I was hearing this part of the presentation. The rest is a little easier. So we're not going to speak about third, fourth, and fifth electron just because I'm lazy. We can get through basic principles only with two. So we declare this functional form, which in some sense it is a product of functions of one argument, one electron wave functions. But it is not product, but superposition of products with swapped order, right? And we just agreed through this little, I wouldn't say it is proof, but demonstration, mathematical experiment, that this is a really good idea, good choice. So we are going to seek for solution of multi-electron wave function in this functional form. And in few minutes, we are going to update it for a larger number of electrons, hopefully. Okay? Declared? Okay. Slater. Why determinant? Any ideas? Slater is the name of a person. You saw the photograph. But determinant, I'm not lucky to know the person with first or last name determinant. Hi, I'm determinant.
Okay, well, I guess I learned this in like quantum one. When you're writing like wave functions, you can represent them in major Z's. I mean, you can represent the Hamiltonian in like a matrix, like a 2x2 or a 3x3 matrix, and then when you apply that to like a wave function, you'll get an energy times that same wave function. Now, in linear algebra, when you're trying to find, like eigenfunctions and like eigenvectors, you like take the determinant of that matrix, set in like equal to 0, and then that's how you find that the energy eigenvalues and eigen.
This is not wrong.
Okay.
But what Kevin told to us deals with one electron quantum mechanics.
Okay.
So all textbooks and like 80% of basic quantum theory or PChem that some of attendees of this class were taking before deal with one electron problems. And what you are telling, there are some basic states, and there is some perturbation. One tries to diagonalize Hamiltonian. And diagonalization includes procedure of finding determinant. This is correct. This is good, but it is not. It's a little different story.
All right.
Now we bring in more than one electron. Yes.
Well, to find a determinant, you take a matrix and you multiply certain elements together and subtract those results from each other. So that's pretty much exactly what you're doing right there. So it's a good way of representing multi-symmetric wave function.
I cannot do it, but everyone agreed. Everyone heard what Nathan told.
Have you found a determinant before?
Well, yeah.
Okay. So if you have, like, in the top row of a matrix, if you have like f of R1 and f of R1 and g of R2, and then on the bottom row you have g of R1. I might be mixing it up.
So
Are you going to mix up the G's and the F's? Different.
Well, so if you have like a 2x2 matrix to find the determinant,
Yeah,
you take this one times this one minus this one times this one. So
what is the determinant of the 2x2 matrix?
It's like a AD minus BC or something like that.
AD minus BC, diagonal minus off diagonal, right?
So if you make those functions match up with the A and D and B and C, right? What you wrote there is the same as that.
Like if you see combination of A, D, B, C in this order, you can, why should I memorize the order? Can we logically go from this line to determinant of some matrix? So if we do see combination of phi 1 of R1 times phi 2 R2 minus phi 2 R1 phi 1 R2, can we make a connection? This will be our A, this will be our D, this will be our B, this will be our C. Right? And just let's distribute this one electron functions in the matrix that we just designed for comfort. I know many of you develop irritated feelings, like any word about matrix cannot make me comfortable. But it is much easier than, much simpler and more comfortable than anything else. Of course, it's better to just sit on a couch with a beer than thinking of matrix. But rather than writing long lines that are hard to memorize, it's easier to put them into this format. So phi 1 R1, phi 2 R2 on the diagonal, phi 2 R1, phi 1 R2 on the off diagonal. And if you take determinant, we will get exactly this expression, right? So Slater took into account antisymmetry, and determinant took into account a comfortable way to represent it. Make sense? It's already here. And if one assumes that each of the phi 1 and phi 2 wave functions are normalized, and one will practice double integral over R1 and R2 of the many electron wave function, one can get that it will be also 1.
Since we're only dealing with 2 electrons, we're not going to have anything better than a 2, bigger than a 2 by 2 in this case.
This is a great homework. Probably not for now, but like next year. Oh, okay.
Oh.
I didn't want to believe that everything what I'm offering is correct. Some people like abstract thinking. Some people prefer very, very practical things. So I have, yeah, this one. So what if our function phi 1 will be sine? Oh, by the way, why sine and why sine functions? Maybe make something here. Please lift hands if those who took some basic level of quantum theory.
Being quantum mechanics 1 and 2.
Yeah. And who never took any quantum? Who never took? If you never took quantum. Okay. So if you are in this class and you didn't take quantum, you are really brave. But if you perform well, it means that you have support for this to be brave. So in the basic quantum theory, there are some favorite problems that everyone solves for little practice. And one of the favorite practical problems is so-called particle in the box, right? So right now, who are my primary target? Kurt, Queenie, Anas, who are lifting hands, right? So if one has very artificial, it's much simpler than any atom or any molecule, just potential V that is infinite if for the box, if x is smaller than 0 and infinite if x is bigger than some number and 0 in between, there are very standard, well reproducible solutions of Schrödinger equation for such model mathematical problem. And they will have shape of sine. And if you offset them by energy, it will be sine with one harmonic, second harmonic, third harmonic, and so on, right? So the sine functions for the particle in the box are good examples of basic quantum theory, right? Now, what if our multi-electron wave function is attempt to put two electrons into particle into the box? By Pauli exclusion principle, you cannot put two electrons into the first state, right? It should be one electron, R1, in state 1 here, and second electron, number 2, into the state phi 2, right? But since we believe in Slater, and since we believe in determinant, the wave function of two electrons should be composed as we already discussed. But here we can put literally. So phi 1 of R1 will be sine of R1, and phi 2 of R2 will be sine 2 R2. Right? If you go higher up in harmonics, here is sine x, here is sine 2x, here is sine 3x. So quantum number just pops up, making it oscillate more frequently. Right?
So they're only signs then?
Huh?
They're only signs, though.
Yes, yes. Well, there is some normalization factor, but we will die if we will and spend waste time.
Okay.
Make sense? Now, let's practice this product. So harmonic number 1, and it's not as long. So function phi 1 is sine of argument. First electron in the first harmonic. Second electron x2 in the second harmonic. Now, since it is function of two variables, we draw along, I swap them. Along one dimension it will be one hump, along another direction it will be two humps. So two-dimensional function, plus and minus. Make sense? If we swap order of the arguments here, second electron in first orbital and first electron in second orbital, then it will be same shape, but it will be rotated by 90 degrees, right? And if we subtract them from each other, it will be like plus minus plus will be 0. Here is the bar telling where is positive, where is negative. So first quadrant, plus minus plus will be 0, green color. Here minus, subtract minus will be again 0. Again, 0 line in the center. Here plus, subtract minus will be big plus. Minus, subtract plus will be big minus. Right? So it is example how two-electron wave function looks like. Right? So it is neither this nor this. It is something more complicated. And if we swap the order of electrons in both of them, this plus and minus areas will swap the order as we require, right? So it is nothing new. It is what we already discussed. It's just a little illustration. Make sense? Good. And if you love MATLAB, here are the just little command lines how to make these images.
So really the vantage point of this is that you'll show kind of sort of a hybrid where things are the further up you go in your, because this looks like to me you're swapping things, but you're also kind of showing a mixture in the last in the last picture there.
Mm-hmm.
So it almost seems like you're covering more area, or you're trying to average things out a little bit nicer. Maybe thinking about
I really do not know how to bring it into common sense,
Okay.
intuitive interpretation.
Okay.
I'm trying to develop some words, but I'm trying not to declare them in public.
Really, this is just
In some sense,
Okay.
it is a rotation of axis of system of coordinates. Before we have x1 and x2, and we always represent it as a product. And here, independent axis becomes x1 plus x2 and x1 minus x2. So we can kind of make rotation in this space.
okay.
Okay. What else? Yes, it is just if we swap sign, I did check that it changes. Okay. Maybe it's enough for today. Right? Let me tell a couple of words more. So if we have more than 2 electrons, we just practice concept of determinant. We list the orbitals, first, second, third, and along, let's say, rows. And along columns, we will list number of electrons. First electron, second electron, third electron, and then practice determinant. And it will give antisymmetric wave function that will obey Pauli exclusion principle.
So you can have a bigger than a 2 by 2, and you have 3
3 by 3 or million by million or whatever,
Okay.
how many electrons.
Just to
you have.
make sure. Okay, yeah.
Yep. So again, what is the benefit? Why we need it? We do not want to argue with Pauli, right? And if you want to, on one hand, on another hand, we need to solve for multi-electron wave function, and on the third hand, we do not have power to do it at once. We need to divide, separate variables. So separation of variables for multi-electron function, just by nature of this problem, is possible only through this antisymmetric shape, which is called Slater determinant. So, and meanwhile, we got some entertainment about hydrogen-like orbitals. So, hydrogen-like orbitals are our building blocks, and Slater determinant is our blueprint. We will fill Slater determinant with atomic orbitals and get, hopefully, wave function. Maybe I did lie a little in the last sentence, but we will see on the next meeting. Any questions about the content? No?
Question.
Yes, please.
So prior to this, we talked about freezing the ions, and we're focusing now on the electrons. Are we going to bring that back together?
Yes, absolutely.
Okay. Good.
At the very last 3 weeks of the class.
Okay. Okay. So now we're just focusing on certain chunks, and this is the Slater chunk is what we're focusing on.
Let me go to the this navigation map. So the 4 chapters. First one about nuclear dynamics, second and third about electronic structure. And after we finish the 3rd chapter, we all will start intensively digging into research projects.
Right.
So there will be a little discrepancy. The class material will be about excited states and optical properties, and substantial part of the research projects will be about simultaneous evolution of electronic and nuclear degrees of freedom. We will not need additional material in class because it will be already covered in previous chapters.
Excellent. Perfect.
Enough. Thank you much for your questions and participation in the discussion. Looking forward to see you same room,
Yes.
5 p.m. tomorrow.
Yeah. That's true.
Oh, thank you.
I had one question, like on the another homework that we for extra points. So how you wanted us to solve that? I just like
Use atomic models.
yeah.
Um,
Those view.
yes, yes, and I was expecting to like print how it looks like. And
How to?
print. Build atomic model, optimize and print.
Oh,
Measure interatomic. Yes.
downloaded it online and I just gave it for relaxation. So I
It's fine,
didn't
it's fine.
understand the questions.
Okay, I'll be more specific next time.
No problem. Like I just feel that maybe you are expecting downstate energy. That's why.
Well, I'm going to ask it in the next round, but I wanted to split building and optimizing
Okay, so
from
you wanted
characterization.
to you wanted us to draw that structure.
Yes.
Sorry, so I didn't.
That's okay. That's okay.
You for the model kids?
Yes, let's walk.
Oh, yeah.
Let's walk together. We'll walk to Dr. Kilina's office first. She has some kits to share that she doesn't need, and if it will be insufficient, we'll go to my office. I have a few more kits that I need back sooner. But
So, kits, yeah. So,
kits, KITS.
So we need enough carbon and hydrogen. Sorry, go ahead.
yeah, I guess I don't. Are they all the same? Whatever. You'll show us, and
Yeah.
I'm sure
So we
we'll
want
be
to be
good.
able to make a long haul. That's the goal.
Are you in a rush?
Me? They're gone, aren't they? They're so good. Yeah, so I'll have you take care of that. Thank you.
Yeah.
We're doing a thing on Thursday, so it's for the kids.
I know you kept saying kids. I'm like, kids? Like,
Kids,
kids.
yeah, not mom
Kids for kids for the
kids
kids.
for kids. Thanks. Have a great night.
You too. Thanks much for.
Yeah, you're welcome.
Okay, so we're good to go?
Yeah.
Okay. So
I need to go work. I need to do stuff. Because if we present it in February, right?
Yeah. Is it end of February?
Yeah, well, the summit or something.
It's after.
There's something in February we would present. And then it's like one thing in March.
I don't know. At this point, I don't know anymore. Dr. Rezlo said, oh, it's empty. I should ask you, thank you. If you knew how, I mean, he just forgot the function, but how to convert directly. Okay, so if I have like an output file from my Gaussian, and I want to convert directly like the last Cartesian coordinates it gave to me to another like mol file or something. He said I can directly use Gaussian to, I can use OpenBabel functionality on CCAS to do that.
Yes.
So I was wondering, how would you go about
Wait.
that?
We didn't have time to go through, but it was kind of my expectation that you'll present to everyone how to use command line Babel.
Oh, command. Well, I'm not.
It's time for you to learn at least for yourself.
Yeah.
I was partially showing it in the lab here.
Yeah.
And we can quickly go over it,
but this one is more about like getting like the so I'm trying to extract the last coordinate I was given on this big output file, right? So I was wondering, will it just naturally go into the last, like my output file, and just extract the last coordinate without any like program or anything, like function?
Well, try to use Babel. Like Babel minus I, Gaussian 09, space, name of your output, space, minus output, XYZ.
So minus I is the function, so give me a second.
Look,
something else missing.
it was in the record. I think it was in the recording of the lab.
Yeah, there was something else missing. That's why I was curious. So I have, this is what we tried. Babel space minus I. Should there be a space in between anything?
No space. But it will not. I'm not sure if it, instead of Gaussian job file, put XYZ here.
So I should put
Output
output XYZ. Okay.
And I will say, if it will not work, I have another suggestion.
Okay.
I'll bring it to.
Because
I'll try to bring it to the lab.
I tried without. I tried this one, it didn't work, so I'll try the XYZ.
It's not Babel who is guilty. It's Gaussian who is guilty.
It's Gaussian.
They forbid people to overuse their format. They have some legal protections.
Okay. All right. Well, I will try it out and I'll let you know tomorrow.
Okay.
Thank you.
Oh, my pleasure. Very soon, I'm almost done.
Where is?
I was curious.
I
Oh, terrible. 0.399.
Any increase in mixing?
I did everything. Well, everything increased, but everything was solid. Drywall and like building and the last building. I did 5,000.
Number of rotation.
Yeah, I went to like 35, 40%.
That's still low. Go to 60, 65. You'll get the data from that. So he just, like what, they just thought of it, just, do this, do that. But what he expects is for us to play around with it, see what can possibly come out of it.
Yeah, I don't understand that, because like Anas's been working on it for like a month, and it's like, I mean, is there a point where you're just beating a dead horse? Is the same, where it's like.
They're just trying to get a better data.
Yeah.
First of all,
Maybe because he is close, right? Because he's close, maybe that's why Russell wants you to keep pushing it.
Yeah.
But at the same time, you can't force something that's not there.
But what Anas has right now is better than what they had.
Sure he does. Oh, I thought there was like even or a little less.
It's a little better than what they had the first time because he added a little bit more relationship in there.
So if it was like 75 and us has what 18?
Probably. The thing was that when Anas did it, even adding Homo, it didn't show up on like one of the descriptors that
Yeah.
But then he added it and it made a significant difference to like his results. So how come you add that, it doesn't show up